Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Have you ever wondered how the majestic mountains got their unique characteristics? The beauty and mystery of nature never cease to amaze. From the towering peaks of the Himalayas to the rolling hills of the Scottish Highlands, every terrain tells a story. But have you ever stopped to think about the forces that shape these landscapes? Enter the world of metamorphism. This geological process is the unsung hero behind the Earth's ever-changing topography. It's the silent artist that sculpts the mountains, valleys and plains over millions of years. Think about it. The grandeur of a mountain range, the lushness of a green valley, the stark beauty of a desert, all are a testament to the power and mystery of metamorphism. This process, dictated by heat, pressure and time, transforms simple rocks into complex structures, giving the Earth its diverse and awe-inspiring landscapes. To unravel this mystery, we dive into the world of geology and explore the intriguing process of metamorphism. Metamorphism, a word derived from Greek, means change of form. But what exactly changes and how? To unravel this mystery, let's embark on a journey deep within the Earth's crust. Picture a rock subjected to extreme pressures and temperatures, unlike anything we experience on the surface. These conditions, intense and relentless, can alter the rock's mineral composition and texture, causing it to metamorphose. Think of it as a rock's rite of passage. The rock, which could be igneous, sedimentary, or even previously metamorphosed, enters a state of flux under these high-pressure and high-temperature conditions. The minerals within the rock start to rearrange themselves, forming new minerals that are stable under these extreme conditions. This process is known as recrystallization. But how does this happen? Well, the extreme pressure forces atoms closer together, while the high temperatures provide the energy needed for the atoms to move and rearrange. These combined forces compel the rock to transform, changing its mineral composition and texture. Now, let's talk about the rock's texture. The pressure exerted on the rock is not equal from all directions. This differential pressure causes the minerals within the rock to realign and form layers or bands, a characteristic feature of metamorphic rocks. This process of realignment under non-uniform pressure is called foliation. So the metamorphic process is essentially a two-stage transformation. The first stage involves the formation of new minerals through recrystallization. The second stage is the structural transformation or foliation caused by differential pressure. Together, these processes completely transform the original rock into a metamorphic rock. But it's important to note that not all rocks undergo metamorphism. Some rocks simply can't withstand the extreme conditions and instead melt, forming magma. This magma can later cool and solidify to form new igneous rocks. So metamorphism transforms rocks, but what causes these extreme conditions? The answer lies in plate tectonics. Our Earth's crust is not one solid piece, but rather a jigsaw puzzle of tectonic plates. These plates, large chunks of the Earth's lithosphere, glide atop the semi-fluid asthenosphere, their constant movement shaping the world we see around us. This movement, driven by the heat from Earth's core, is a key player in the drama of metamorphism. But how do these plates contribute to metamorphism? It's all about the conditions they create. As these plates collide, pull apart, or scrape past each other, they generate the high pressure and temperature necessary for metamorphism to occur. Let's take a closer look at the three types of plate boundaries and the unique metamorphic processes associated with each. First, we have convergent boundaries where plates crash into each other. This collision can form mountain ranges and trigger regional metamorphism, where rocks are transformed over large areas due to intense pressure and heat. Next, we have divergent boundaries where plates pull apart. Here, new crust is formed as magma rises to fill the gap. The heat from this magma can cause contact metamorphism, a localized process where rocks are altered by the heat of nearby magma. Finally, we have transform boundaries, where plates slide past each other. The intense pressure and friction here can lead to dynamic metamorphism, where rocks are altered mainly due to mechanical deformation. But it's not just about the pressure and temperature. The movement of these plates also aids in the transport of materials. As the plates move, they carry the rocks with them, exposing them to different environments and thus different metamorphic processes. This movement can transform a simple limestone into a majestic marble or a humble sandstone into a striking quartzite. Plate tectonics thus sets the stage for metamorphism. But how does the material transport happen during this process? Stay tuned as we delve deeper into the fascinating journey of rocks through the Earth's crust. The metamorphic process is not just about change, it's also about movement. When we talk about metamorphism, we often focus on the transformation of the rock's minerals and structures. However, equally important is the process of material transport that takes place during metamorphism. It's a fascinating journey of elements, fluids and gases moving within and out of the rock that significantly contributes to the metamorphic process. At the heart of this transport process are fluids. These include water, carbon dioxide, and other volatile substances that seep into the rock through tiny spaces between grains or along fractures. As these fluids move, they carry with them elements from one part of the rock to another, or even out of the rock entirely. This movement of elements can lead to changes in the rock's overall composition, further driving the metamorphic transformation. The role of gases in material transport during metamorphism is also noteworthy. Gases like water vapor and carbon dioxide can dissolve certain elements and minerals, transporting them within the rock. When these gases eventually leave the rock, either through seeping out or being squeezed out by intense pressure, they take with them these dissolved substances. This not only alters the rock's composition, but also influences the surrounding environment. Imagine this: a rock buried deep underground, subjected to intense heat and pressure, undergoing not just physical and chemical changes, but also experiencing this incredible journey of fluids and gases, moving within and out of it. It's this transport of elements that truly completes the metamorphic process, making it a dynamic rather than a static phenomenon. But the journey of metamorphism doesn't end here. The next phase is the PTT path, which stands for pressure, temperature, time path. This path traces the changes in pressure, temperature, and time that a rock experiences during its metamorphic journey. Now that we understand the mechanics of metamorphism and material transport, let's talk about the PTT path. The PTT path, or pressure, temperature, time path, is like a rock's personal diary. It chronicles the history of a rock, marking the changes in pressure, temperature, and time that it has experienced. In essence, it is a rock's autobiography, penned in the language of geology. To understand the PTT path, think of it as a map that traces a rock's journey through the Earth's crust. Each point on the path represents a specific moment in the rock's life, with the coordinates of pressure and temperature describing the conditions. The order of these points, following the arrow of time, paints a picture of the rock's metamorphic history. The significance of the PTT path lies in its ability to reveal the sequence and conditions of metamorphic events. By studying these paths, geologists can piece together the tectonic history of a region. The changes in pressure and temperature can indicate whether the rock has been buried deep within the earth, heated by an intruding magma body, or uplifted to the surface. But how do geologists decipher these rock diaries? They do so by studying the minerals within the rock. Different minerals form under different conditions of pressure and temperature, and their presence can give clues about the conditions at a particular point in the rock's history. For example, the mineral garnet often grows during metamorphism. By studying the composition of garnet, scientists can estimate the pressure and temperature at the time of its growth. Similarly, the presence of other minerals, such as staurolite or kyanite, can provide additional clues about the PTT path of a rock. In regional metamorphic terrains, the PTT path is especially useful. These terrains have experienced large-scale tectonic events such as mountain building that have caused extensive metamorphism. The PTT paths of the rocks in these terrains can reveal the history of these tectonic events, helping geologists to understand the forces that have shaped our planet. Thus, the PTT path provides a glimpse into the past, telling us the story of a rock's metamorphic journey. From the towering mountains to the smallest pebbles, metamorphism has a hand in shaping them all. we've journeyed together through the fascinating process of metamorphism, where everyday rocks undergo intense changes under pressure and heat to become something entirely different. Diving deeper, we've explored the pivotal role of plate tectonics in this process. The constant motion of these giant slabs of the Earth's crust creates the perfect conditions for metamorphism to take place, leading to the birth of new metamorphic rocks. We've also unraveled the intriguing concept of material transport during metamorphism, where elements and compounds are exchanged between the rock and its surrounding environment, adding layers of complexity to this transformation. Lastly, we've navigated the PTT path, illustrating the journey of a rock in a regional metamorphic terrain as it travels through varying pressures, temperatures, and times. Next time you see a mountain or a simple stone, remember the extraordinary journey it has undergone and the fascinating story it has to tell. Often overlooked, water plays a crucial role in metamorphism, acting as a catalyst in the transformation of rocks. It's not just about heat and pressure. Water too has a significant part to play in this geological drama. Firstly, water facilitates the movement of ions within the rock. This fluid movement enables the recrystallization process, a key aspect of metamorphism. It's like a dance, with water leading the ions through the rock, allowing them to reposition and form new structures. Secondly, water helps in the formation of new minerals. How, you ask? Well, it provides necessary elements that combine with those in the parent rock, giving birth to new metamorphic minerals. Think of it as a delivery service, bringing in essential supplies for the creation of these new entities. Lastly, the presence of water can lower the temperature at which certain reactions occur. This means that metamorphism can happen at lower temperatures than it would without water, speeding up the metamorphic process. It's like adding a turbo boost to a car, accelerating the transformation. So next time you think of metamorphism, remember that water is not just the elixir of life, but also a key player in the metamorphic process. Its silent yet significant role in shaping the Earth's crust is a testament to the intricacies of our natural world. From the role of water, let's now dive into another fascinating aspect of metamorphism: metamorphic facies. These are a set of mineral assemblages in metamorphic rocks formed under similar pressures and temperatures. So what makes them important? Well, they provide invaluable clues to the metamorphic conditions that existed when the rocks formed. It's like a geological detective piecing together the story of our planet's past. There are several types of metamorphic facies, each unique in their mineral composition, reflecting the specific metamorphic conditions they were subjected to. For instance, the green schist facies, which forms under low temperatures and pressures, is characterized by the presence of green minerals like chlorite and epidote. On the other end of the spectrum, we have the granulite facies, formed under high temperatures and pressures and dominated by minerals like garnet and pyroxene. Each of these facies tells a different tale of our Earth's geological history. But how do they help us in interpreting the geological history of an area? Well, by studying the minerals present in a rock and knowing the conditions under which these minerals form, geologists can deduce the pressure-temperature conditions that existed during the rock's metamorphism. It's like a time machine transporting us back to the time of rock formation. To conclude, metamorphic facies serve as a window into the past, helping us understand the metamorphic conditions prevalent at the time of rock formation. They hold the secrets of our Earth's past, waiting to be unlocked by those curious enough to investigate. As we continue our journey through the world of metamorphism, we now find ourselves in the realm of metamorphic zones. What are they, you may ask? Well, metamorphic zones are regions within a metamorphic belt where specific metamorphic minerals known as index minerals are found. These index minerals act as geological signposts, indicating the metamorphic conditions prevalent in that zone. For instance, the presence of the mineral garnet in a metamorphic rock indicates that the rock was subjected to a certain range of pressure and temperature during metamorphism. And this is why metamorphic zones are so crucial in our study of metamorphism. They allow us to map out the metamorphic history of a region, providing insights into the geological processes that have shaped the Earth's crust over millions of years. Identifying these zones is like solving a complex puzzle. Geologists carefully study the distribution of index minerals in metamorphic rocks. and use this information to delineate the different zones. They then correlate these zones with the pressure-temperature conditions at which these minerals form, thereby reconstructing the metamorphic conditions that existed during the formation of these rocks. So in essence, metamorphic zones serve as markers guiding us through the metamorphic history of a region. With each zone, we peel back another layer of the Earth's past, gaining a deeper understanding of the dynamic forces that have shaped our planet. The study of metamorphic zones, therefore, forms a critical part of our journey to unravel the mysteries of metamorphism. As we progress further in our exploration of metamorphism, our next stop brings us to the concept of metamorphic grade. This term refers to the intensity or degree of metamorphism that a rock has undergone. Just like grades in school indicate the level of knowledge acquired, the metamorphic grade indicates the extent of transformation a rock has experienced due to changes in pressure, temperature, and chemical environment. The metamorphic grade of a rock is intrinsically linked to its mineral composition. As we move from low-grade to high-grade metamorphism, the mineral assemblage within the rocks changes. For instance, a low-grade metamorphic rock may contain minerals such as chlorite, muscovite, and biotite. But as we move to higher grades of metamorphism, these minerals are gradually replaced by others like garnet, staurolite, and kyanite. This change in mineral composition is a response to the increasing pressure and temperature conditions that the rock is subjected to. But why is understanding the metamorphic grade important? Well, the metamorphic grade provides critical insights into the pressure-temperature conditions experienced by a rock during its metamorphic journey. By studying the mineral composition and the metamorphic grade of a rock, geologists can reconstruct the metamorphic conditions that the rock has experienced. This information can help us decipher the geological history of a region, revealing the tectonic events that have shaped the Earth's crust over millions of years. In essence, understanding the metamorphic grade of a rock is like reading its autobiography. It allows us to trace back the metamorphic path that the rock has followed, from its birth in the Earth's crust to its present state. Each grade, each mineral change tells a story of transformation, resilience, and evolution, echoing the dynamic forces that have molded our planet. And that, dear viewers, is the fascinating story that the metamorphic grade helps us unravel. From the metamorphic grade, let's move on to another crucial aspect of studying metamorphic rocks, their textures. Metamorphic textures are the physical and visual characteristics of a rock that provide clues about the conditions under which it has metamorphosed. Understanding these textures is like deciphering a secret code, telling us the unique metamorphic history of the rock. There are several types of metamorphic textures, each revealing something different about the metamorphic conditions. For instance, a foliated texture, characterized by a layered or banded appearance, indicates that the rock has been subjected to differential pressure. This is a common texture seen in rocks that have undergone regional metamorphism, such as gneiss and schist. On the other hand, a non-foliated texture, where the minerals are randomly arranged, suggests that the rock has been subjected to equal pressure from all directions. This texture is typical of rocks that have undergone contact metamorphism, such as marble and quartzite. But how can these textures help us? Well, by studying metamorphic textures, we can identify the type of metamorphism a rock has undergone. For instance, a foliated texture could suggest regional metamorphism, while a non-foliated texture could hint at contact metamorphism. These textures can also help us estimate the pressure-temperature conditions during metamorphism, providing vital clues about the tectonic processes that have happened in a region. In essence, metamorphic textures are like fingerprints. Each texture is unique and tells a different story of metamorphism. By studying these textures, we can unravel the secrets of the Earth's crust, gaining insights into the dynamic forces that have shaped our planet. So the next time you come across a metamorphic rock, remember its texture holds a story waiting to be told. Thanks for watching us. Share our videos, subscribe our YouTube channel, and press the bell icon and stay curious for new uploads.